We're going to continue in the world of equilibrium in chemistry now. If you, just to recap, well, first of all, let's say what the topic is. The topic here is going to be the equilibrium constant. Equilibrium constant. And let's call it K subscript. To be advised on the subscript. Okay, we're going to get there and see. There's a couple of them, but don't worry. Now, remember what we said. We said that at equilibrium, the rate of the forward is equal to the rate of the reverse. We also said that at equilibrium, right, we still have in our tank, you remember, we have molecules. Let's just take the nitrogen and the hydrogen one. N2 gas plus H2 gas going to NH3 gas. There's a 2, there's a 3. And we said 1 plus 3 goes to 2. Now, what do we mean? When I say we've got equilibrium, inside the tank, there is still some nitrogen, hydrogen, and ammonia, all coexisting at the same time. We spoke about the possibility of withdrawing product because that's what we're doing. Remember, we said this is reactant, this is product. Those there were the rates. Now, at equilibrium, there is some nitrogen, there is some hydrogen, and there is some, this is at equilibrium. In other words, the equilibrium reactions are not reactions at this point that we're going to run to completion. We are making a thing that it's in the process. And at that point, the reaction has essentially stopped at equilibrium, hasn't it? Because if one molecule of water is leaving, one molecule of water is coming back in our kettle analogy that we started off with. So in this equation, an atom, a molecule of nitrogen is splitting, joining up, some hydrogens are splitting, joining up, 3 hydrogens are joining with 1, like so, and becoming an ammonia. And the rate that this happens, or rather the ratio that it happens over there, is critical here, right? We cannot have half a molecule of nitrogen reacting, leaving N sitting in the tank, right? Now, what do? We say, right, therefore, at equilibrium, there is concentrations remaining. Right? Now I'm going to just use a hypothetical reaction. This is A moles of A plus B moles of B going to C moles of C plus D moles of D. This is my reactant, and this is my product over here. Right? Sorry, that was me and my timer again, forgot it. So we've got reactant going to product. There we go. That's our standard reaction. Now, if at the end of the day, we come and we say, right, the reaction now, that and that are equal, therefore the reaction is at equilibrium. At equilibrium, what am I saying? I'm saying at equilibrium, I have got a concentration of A left, I've got a concentration of B left, all right? And I've got a concentration of C, and I've got a concentration of D. These were produced, these were left over concentrations, right? Yes, in the process, just to bring in something, I used up reactants. Didn't I? Obviously I did. If I'm going to paint a wall, I'm going to use paint. Therefore, my product is a painted wall. I've used paint out of there. Now, and I know that sounds like belaboring, but trust me, it's an important concept that we have to go through when we do a little table coming. Now, at this point here, we have got something that we call the equilibrium constant, and I am going to call it K. All right? You might see in some of your textbooks K forward, K reverse. Just for the timing, let us just define. This is the definition. let's define K. K is a number. And the number is the concentration, okay, of C to the power of C multiplied by the concentration of D to the power of D divided by the concentration of A to the power of A multiplied by the concentration of B to the power of B. Can you see it's the concentration of products divided by concentration of reactants? All right? We're just going to define it like that. This term here we call the equilibrium constant. A very important part of life when we're talking about our chemistry. Now, the equilibrium constant is the concentrations. And remember here, concentrations are measured in moles per decimeters cubed. If you are not given decimeters cubed, you can assume 1. Okay? Just use a 1 for the moment. Okay? But generally speaking, we're going to give you or you will be given the actual volume that you need to use. Now, this here, let me just show you another thing. This thing here is called the expression of mass action. So in chemistry, that is the expression of mass action. Okay, the next question that you're going to ask me is you're going to say to me, right, that's the expression of mass action. What about the units of K? The units of K there are none. Why? Because, remember, we are going to say, let us say K is a simple one, is moles per decimeter cubed, okay, and it's a 1-to-1 reaction over moles per decimeter. That's all going to cancel out. Let us say for a different reaction, K could be moles per, moles per decimeter cubed divided by moles per decimeter cubed over there. And here you're going to get nonsensical units. Therefore, we omit units. We omit the units on the K, right? The last part is, I said at the top, I said some kind of subscript, we give it Kc. Kc means it's at equilibrium. Please note, Kc is the equilibrium constant itself. All right? So, essentially, you've got that. Now, I'm not going to go and do an example which is very, very straightforward, where we get given a concentration and we get given that. But let's just have a look. Remember, if they say, okay, if they give you concentration of this is equal to, let us say concentration of product squared divided by concentration of reactant, okay, you would calculate that, and divide. All right? If you had different products, you just plug it into that formula and you would divide it. Now, I do need at this point to say that if Kc is given and product is given, then you can calculate this, right? You can calculate that one. It's one missing. So whenever we're given concentrations, we always write the expression of mass action. We then put in the concentrations we are given. Please be careful. 1 decimeter cubed is 1 liter. Please remember that. And what do? We always convert to decimeters cubed, all right, or liters. But decimeters cubed is generally what we've been working with. Now, all right, what if we have got a situation where we've got solids or liquids. Let's introduce solids or liquids. In other words, the S or the L in the equation. Right? So we have, for example, we have a situation, let us say, where we put, I don't know, HCl plus H2O liquid, all right? You put that together, we know what we're going to get, all right? We're going to get H3O plus Cl minus, right? Now, at equilibrium, we're going to get to this one, but please, the solids or the liquids, you treat as one. Therefore, give them the value of 1. Okay, not 0. It is 1. Because if it's 0, all right, you're going to want to be dividing by 0 and it's going to confuse you. Or you can, instead of the value of 1, you can omit them. Okay, now everybody's got their own particular take on what. I do not like the omit them, because that means that I haven't completed my task, if you know what I mean. I don't think that we should say omit. I say call them 1, because then you've actually given them a positive value. You've said, right, that is 1. Because if you tend to admit them or omit them, we tend to think of it as 0, and it's not. Okay. Therefore, in the calculation that we have over here, I have to fix that up again, don't I? In the calculations, we now can say if there's solids or waters, we write them as 1. Okay? Now, please remember, all right, we are going to look at Kc is always quoted at a specific temperature. NB. Okay. It is temperature dependent. What am I saying? I'm saying that if I change temperature, then we change Kc. All right. It is not. It's not going to be pressure or concentration, because I'm not going into that now. But essentially, the ratios stay the same. Therefore, it doesn't affect the Kc. But the temperature we're going to do. Okay. I might, as an additional part to this, do the proofs where we do it. But at this point, it's not really necessary. As long as we know, change the temperature, we change Kc. That is why you will see Kc always given for a specific value. Now, let's look at the equation of Kc. All right, let me rewrite the equation. Kc is equal to, I'm just going to write products divided by reactant. All right. Okie dokie. Now, let's just look at something. Let's go back to very, very early on when we actually looked at ratios. All right. If, let's call this the numerator and the denominator. If the numerator is high, therefore concentration of products is high, then Kc is large, isn't it? If the numerator is high, okay, Kc is going to be large, because it means lots of product. Okay. If the numerator is high, it means there's lots of products. Therefore, okay, it means that Kc is large, right? So there's the two plays here. If Kc is large, it means you get lots of product. If Kc is small, there's little product. So we say if n, the numerator, is small, or denominator is big, you can put in your denominator small, then it means that the products are little. And not as in little, but are little concentrations, let's say. Therefore, very small Kc. So the value of Kc, let's just leave it. The value of Kc at any point, at any temperature, is a very good indicator as to how this reaction is going, isn't it? If Kc is 1,000, it means actually that you have 1,000 times more product than you do reactant, right? So it means that the reaction is, you've got a high yield. What does yield mean? Well, if you go back, you'll see that the yield is the expression to you how much product you get out from the reactants. So in the situation that we're in here, the ratio is very important, right? It means you get a high yield. So if Kc is high, it means a high yield. And the high yield is actually the objective. Okay, controlled. But you want a high yield. Because why? Because it's product. That's what you're trying to make, isn't it? The objective of doing the experiment or to doing the process is to get the product out at the end. Therefore, what we want is we want to get as high yield as possible economically, all right? So we are targeting to get the Kc high. So we have to look at the factors that are going to affect it, okay? And that's going to be temperature. Let us just examine, okay? I've done that there. Right, let's examine now. What about, I said earlier, what about we put, so that was Kc for general reactions. All right? In other words, for any reaction, but it must be equilibrium. Okay? Kc does not apply if it's not at equilibrium. You know, and okay, that could be a multiple choice question, but generally speaking, you're not going to be given a Kc that's not at equilibrium because the Kc is the equilibrium constant itself. So moving along, that's Kc for a general. We're now going to look at specific reactions. I mentioned earlier that we say specific reaction number one, let's look at acids, right? Because we're looking at the stuff that we've been working with for the last years, and acids and bases are a big portion of our work. So what we do is we say, let's have a look at acids now. What happens when I put an acid plus water? I get what? The process that occurs is we get the process of ionization, correct? Ionization. The acid ionizes in the water. Ionize means it breaks up into its ions. Therefore, let's just take a simple acid like HCl, all right? Aqueous plus water, H2O, liquid, goes here to what? The H splits up, just to recap, into an H plus, there's its ions that it makes. And the water stays as it is still. The hydrogen then links up to the H2O to form H3O, which is the hydronium ion, isn't it? H3O plus, and I get the Cl minus coming up over there like that. That's what happens when an acid ionizes in water, right? Now, when this happens, right, essentially, let's consider we've got our tub and we put a drop of acid in there. That drop of acid spreads throughout the entire container or the entire liquid. All right? Obviously, then we get a concentration, moles per cubic decimeter, don't we? These acids, when they are ionizing, I always interchange that. When they ionize, we actually get an equation. This equation here, I wrote equals, this equation here is actually, it's an equilibrium reaction. Because if I remove the water, I get the acid back. I can separate them out. Granted, you're not going to get that if you've burnt a piece of wood, obviously, but with an acid, you can separate it back out. You can get the acid back. So therefore, it's an equilibrium reaction. Therefore, what happens? Here we've got a straightforward 1-to-1 ratio. Always remember we put in the mole ratio. 1, 1, 1, 1, like so. Like that, right? So got 2 moles, 2 moles. That's important. The next phase of this is to say to ourselves, right, let's do the expression of mass action. Expression of mass action is Kc. We are now at equilibrium. I therefore say the concentration of H3O plus ions multiplied by the concentration of Cl minus divided by the concentration of HCl multiplied by the concentration of H2O. Okay, so what have we got here now? Right. We've basically got, okay, we've got a straightforward, what did we say? Water was a liquid. So what do we do? Well, what we do with the water is we say, all right, this water here I use as 1. I use it as 1. Therefore, it removes itself and we get the H3O plus multiplied by the Cl minus divided by the HCl, like so. Remember, the HCl is aqueous. Now, what do we do next? That is the Kc for that reaction. Because it's an acid, we say its Ka is equal to the concentration of the H3O plus multiplied by the concentration of the Cl minus divided by the concentration of the HCl. A, obviously, for the acid. What are we going to go now? We're going to now say, all right, this is a specific equilibrium constant for acids. It's quoted at temperature, all right? Very often I get room temperature because that's what you're going to be using it. You're not going to be heating it specifically, but in some of the processes we are going to. You're going to get acid as a gas. Remember the hydrogen iodide? There's this one here. H2 plus I2, both gases, going to the formation of, and we have done this one, 2HI as a gas. There's an equilibrium, and there's my acid, hydrogen iodide on that side. The Ka over there tells us, thus, it says, if, wait, let me just say, now let me ask you, if Ka is large, big number, what does it mean? It means lots of product, because this is concentration of product over concentration of reactant, isn't it? Can you see? It's always easier when you actually just do the product reactant or the forward reverse in all of this equilibrium chemistry. Just makes it, I don't know, tidier, and we just don't miss anything. Lots of product. Okay? Lots of product, therefore, ionizes readily. Okay? Make lots of product. This is a critical portion for acids and bases coming, because it's got to do with pH, okay, which is what we're going to be talking about in this section on acids and bases. So it ionizes readily. Well, that means I get lots of product and not much reactant left. Okay? The higher the Ka, right, the more product, the less reactant. Because remember, you started off with this, all right? And if all of that has been split, there's nothing of this or very little left at the end of the day. But now what if Ka is small? If Ka is small. Okay, maybe something times 10 to the minus 3. Okay, very little product. This applies to anything again. Remember, it's the same concept. I'm restating it for an acid. Very little product, okay, and therefore lots of reactant. Okay, which means that, and this is where we define it, this here is a strong acid, okay, and this is a, you got it, weak acid. And all these years you've been wondering what the difference between a strong and a weak acid is. Essentially, these strong acids, and we're going to cover them again, but they are your HCl, HNO3, H2SO4, there's H3PO4, those are the one, and there's perchloric acid, which we'll get to. Okay, it's not critical right at this point. These are strong, and then our weak are mainly organic acids. Okay, let's call it citric, because these are all we know. Acetic, remember acetic acid, vinegar. Acetic acid in water is vinegar. All right, I think it's ethanoic, methanoic, right? So yeah, let's just say it's one of these guys there. All right, okay, come here, 1O, OH. Am I right? Single bond, Kevin. Okay. 1, 2, 3, 4. There we go. Right. These are generally the weak acids. The acid came from there. Remember when we did esters? Now, these are the strong acids. The acid comes from the front. There it is. Okay. As soon as this is finished doing the autosave, it will show you. Now, on our weak acids and our strong acids, that tells us that our Ka high strong acid, all right, so let's go Ka high, okay, lots of H3O plus, okay, low is little concentration of H3O plus, and we're going to measure these in future pH. Okay, now you'll get to that in a minute. We'll see later in acid-base calculations. All right. Okay, so what about, if I said to you then, well, what about H2SO4? Well, let's put H2SO4 plus H2O and put that in water. What do I get? This here ionizes to give me 2 H pluses and an SO4 minus 2. Therefore, I now need to create this one. Each one of those needs an H2O, doesn't it? Because it's going to become an H3O, and that's going to become another H3O plus. So I'm going to create 2 H3O pluses. This is a diprotic acid. We're going to get to that. And I'm going to have then an SO4 minus 2 at the bottom. If I do Ka for this guy, now remember I'm going to have the concentration of H3O squared multiplied by the SO4 minus. That minus 2's got nothing to do with it. It's the figure in the front. It's the mole ratio. Because what I am saying is 1 mole of this plus 2 moles of that is going to go to 2 plus 1. So every mole of acid dissociates or ionizes gives us 2 moles of hydronium ion. And lastly, just to complete it, we say at the bottom here, we've got our H2SO4. Can you see the use of the exponent there? This is going to be a high number. Okay. And we're going to then say it's the acidity, the pH is going to give us that. The last one, I think, oh no, there's actually 2 more. I'll do those on the next section, right? Essentially, thus, we're saying that with our equilibrium constant, where we are is we are looking at the dissociation of sub things or the ionization of some things, right? We're looking at a splitting apart. We're actually looking at the dynamics of the reaction itself. What do? Step 1, balanced reaction all the time. Number 2, mole ratio underneath it. Number 3, look what you are given. If you are given the concentration at equilibrium of this one, all right, that one, you can go and work out the K. Remember, that's Kc. If it's an acid, it's Ka. And understand, the higher the K value, the more product you get, the higher the yield, which for acids is very specific. It gives us a higher concentration of H3O, which is what we're going to be interested in the future. Next one, I'm going to look at the dissociation constant of water, Kw. Then we're going to look at solubility product, Ksp. Okay? These are all the same forms of the equilibrium constant. And we'll do some examples when we get to the end. Just always go back to first principles when you're looking at this, and don't get confused by it. Just look at it. Where's the trick going to come? A solid and a liquid. Aqueous and the ions themselves, cool, we work with those. Solids, liquids, we call them 1, because they're not going to play a role in my K value. Cheers, I'll see you in the next one. We'll carry on with those. Thanks for watching. Have a good one. Cheers, bye.